Okay, I think I finished the tesseract program, so I thought I would make a short video to round that off, showing the result. Let's just run the program. Okay, so here we have a 3D projection of a tesseract. And the tesseract has 4 edges, so four axes, obviously. Let's call them the x-axis, the y-axis, the z-axis, and the cyan axis, because I give it a cyan color. And then the tesseract is a 4-dimensional cube, hypercube, has of course edges, length 1, so those are finite, and after projection onto the hyperplane, which is a 3D volume, they are still finite. And then the edge along the x-axis is called red, and then green for the y-axis, blue for the z-axis, and cyan for the 4th axis. It is obviously not so surprising that even in 3D, well, you see a 2D image, but I can rotate the 3D thing that this is with these 2 sliders, and then maybe you see that it is 3D. And despite, yeah, it's the perspective changes suddenly. You think it's in a certain order, but then if I rotate it long enough, you start to see what the rigid 3D object actually is. There's nothing getting longer or shorter. It's just a 3D object that is rotating. You can also rotate it like this. Still rigid, still the same object. It does wiggle a bit though. Yeah, now you can see here red wasn't as short as it seemed to be at first. I thought it was much shorter. So if I rotate it like this and then like this, you must be able to get completely rid of red, right? Yeah, here. So, oops, up and down. So now this red edge is just perpendicular to the screen. That's why you don't see it. But there are 2 dimensions perpendicular to the screen. So it lays in a plane, and the whole plane is perpendicular to the screen. That's why it appears to be short. I can even make 2 of them short. No, that's nonsense. Yeah, well, I could, but then you have a square. If I make one of the 4 dimensions very short, so purely perpendicular to the screen, then at that moment, what is left is a cube, right? So yeah, let's try to make that indeed happen. Like no more red thing. So pixel by pixel. Short enough. So you see now it looks like a cube. That is obviously because the 4th dimension got well hidden by projecting the tesseract onto a 3-dimensional volume. Oh no, that is not true. It's still that object that we just showed, which also has red lines in it. But then after projecting it onto the 3D volume, I projected again on a 2D plane, namely the screen, and that projection then totally got rid of it, of the red line anyway. Now, there must be a way to get rid of it during the first projection already. So these sliders, or the first 3, rotate the hyperplane, so the 3D volume, inside the 4-dimensional space. So let's orient this again so that we can see all the projections of all the colors. Now I'm going to try to rotate the tesseract such that red disappears again. Okay, so now the shape changes because this is now we rotate the four-dimensional object, and then the projection onto the 3D space, well, changes, you know, just like the shadow shape of if you put a 3D object in a light beam, you look at the 2D projection, the shadow. Then by rotating the 3D object, you can change the shape of the shadow. And in this case, where the shadow is a 3D object, so we can change that. I'm going to rotate it such that the red lines are non-existent anymore. I have to try that out. No, I just made blue and red parallel. That's not what you want. Yeah, I have no idea, as you can see. Okay, this might be good. It might be that it's gone now. It's actually very likely because the first one is 0. I think the first one, putting the first one at 0 is exactly what you need. Yeah. It's almost cheating, but yeah, now having this angle being 0, one axis is perpendicular to the hyperplane. So then what you end up with is a cube. So it doesn't matter that I rotate this thing now, it just, red is just gone. But yeah, you don't see the other colors anymore because I'm using the magenta here, dark magenta, for the edges, for the intersection between the hyperplane and the tesseract, which is now also on top of that exact cube. So the whole thing became magenta. However, we can make that disappear by shifting this to all the way down. So yeah, you see that there is exactly 3 colors left. The red one is gone. Should have done that immediately. It was just confusing, that intersection. So we can view the cube from all sides, and the cube itself is the projection, yeah, of the tesseract. And only if I make this alpha angle a little bit larger than 0, then we see that it is a tesseract. And now we have 2 cubes that are very close together, where the corners are connected with a red line. And that means that this cube, so one of the cubes, is the shadow of one side of the tesseract, and the other one is, let's say, call it the bottom, or it's red was X, so call it left. Nah, I'll call it bottom, or it doesn't matter. So this is the bottom, and then the other one is the top. And because we are holding it such that the bottom and the top are almost above each other, and then we project from top to bottom, they almost fall together, yeah, but not quite. So it's funny that you see really, well, 2 cubes close together, where one cube is the bottom and the other one is the top, as it were, of the tesseract. And if you rotate the tesseract even further, then those go apart from each other. More and more apart, and more and more apart, and more and more apart. And now they have completely separated. So this one is one side and this is the other side. Yeah, and then we have two other rotations that you can use. This one is deforming stuff in a non-intuitive way. See what it actually looks like again in 3D. So it looks like two blocks almost on top of each other, and then connected with these lines as well. Okay, now the fun thing is that these three sliders actually give me a vector pointing through the center of the tesseract, and I only, with these three angles, I only determine the direction that it points in. And then with a single vector you can define the hyperplane, provided we also provide a point where it goes through. So the offset here makes our volume shift through the tesseract. And now it's exactly outside the tesseract, so there is no intersection. But if I move it a little bit in it, I'm baffled that there's still nothing visible. Oh, there it is, finally. So now our volume starts to touch one corner of the tesseract. It just dips the corner into it, and then you get 4 intersection points with the 4 edges that are connected to that corner. And then I draw lines between it. And the funny thing is that this, it's a sort of it's a tetrahedron, but then deformed, I guess, is a 3-dimensional object. Now, as long as these green points don't hit another corner, I can just blow it up, and it just keeps having the same shape. So I move it in further and further and further and further and further and further. And then you can see that it is indeed some kind of, what's a 4-pointed something. And that is really a 3D object. So there is no double projection here. It is the intersection of the volume inside this thing is the intersection between our hypervolume, which is 3-dimensional, and the tesseract inside of the tesseract. Therefore, it is a 3D object. So you can look, look how that looks, as it were. And then if we move even more of the hyperplane into the tesseract, then it's going to hit one of the other corners, like here, for example. And these are 1, 2, 3 lines, and then what happens is those 3 split up and follow the other line. And that is the other 3 lines, and that is really not that hard to understand. If you think about the normal cube passing through, let's say, you have a normal cube and you pass a plane through it. Then at first, if the plane hits the corner, so ignore these sign lines here, just this block here. When we move a plane here, and it touches this corner, then you have 1, 2, 3, obviously, intersection points, whereas something that exists of 3 triangles. Yes, and the intersection between the plane and the cube itself is just a triangle, just these intersection points connected. So a single triangle. You can make that larger. You have a triangle here, and it grows until you have a triangle like here. Yes. And then if you move it even further, then this intersection, the plane that was intersecting that edge, then the red X and the green X, now it exchanges intersecting with the red edge for intersecting with the green and the blue edge. So 1 becomes 2. And also it looks like it got cut off, because if this side was not there, but the red edge was continued, then we would still have cut it a little bit past this point. So these three, I'll move it back a little bit again. See, these three lines here, they come together on this edge, and reaching this point just means that the tesseract ends in this point. And from here there are 3 axes that are all 3 perpendicular to blue, just like the blue and the green here are both perpendicular to the red. And then that's where it gets cut off, as it were. So you can also already do that here. You just cut it off, and then you end up with a triangle at the end, because it goes further than it is possible. Yeah, so this keeps shifting, it keeps shifting to the end, and then it goes past that point. So now it would be something here, but yeah, there is no tesseract there, so that's why it got cut off. And now we can continue. Same thing happens here. So yeah, we hit the other line. Say the plane is now all the way here, and then it hits this corner. So now the green is divided into 2, and here we have the cyan one is divided into 3: red, green, and blue. Happens. The same thing happens there. And the next one is, I guess, well, even this happens before that one, but okay. Let's just look at the top here. That one happens the same, of course. It just hits it and then splits into 3, and then here the same thing, splits into 3. Okay, but what happens if our if we one of those 3 things hits another corner? Well, so very surprisingly, they always come in pairs now. It is possible that this point comes here before that other point is there. Okay, so they just both reach there, and then they reach together, they reach it, and then they follow the other 2. So they came in via red and blue, and then they depart over green and cyan. Yeah, that has no good equivalent thing in 3 dimensions. See, it would have been nice if I also had a 3-dimensional example. I only have this 4-dimensional thing. Well, you can make a 3D like this, but then there's nothing to shift, I think. No, just bang, we are there, or we're not there. Yep. No, I wanted to make this a short video. It already failed. Okay, so they split in 2, and then well, here there's still 3 lines, so these split into 3 from 1 to 3. Oh, that's still from the beginning. Okay, so we grow from this point, and the first corner makes it split into 3 points. There, there, and then if we reach a point, if 2 points reach a corner at the same time, it just follows the other 2. I swear I did eat. I don't know why it's whining. I did eat the wrong thing though. Yeah, well, it's Christmas almost, you know. Shouldn't have done it. But what is this? Yeah, this one splits up, and then that one splits up, and then it just get together again. So we have 2 become again 2, but over the other 2 axes. And it does that everywhere, and then we come together again with 3 points. Next, so 3 points come together and become 1. And then there as well. That one still has to split into 2 points, and then here we have again 3 points. Yeah, this looks like this one is so far away that it's not gonna make it, but this is a cut. By the time these 2 reach that point, there is no cut anymore. So I mean, like the 3D cube, you cut with a plane and you move the plane to a corner. By the time the plane reaches the corner, the intersection with all the 3 edges reach that corner at the same moment, and then the plane is no longer inside the cube, obviously. So this as well. Oops, we went that way, and all 3 there, and now we have 1, and then here as well, the last one, and then we leave the whole tesseract on the opposite corner. So okay, for example, we now know that this was the place where we exited. So we can easily find the opposite corner, and you just follow every color once. Doesn't matter which one. But let's say we follow X and then Y and then Z and then the sign one. So X, that's red, green, blue, sign. So that's the opposite corner. Or we could do blue and then green and then sign and then red, but you end up in the same thing, of course. So if we go all the way down, then this is the point where it's going to disappear again. Okay. Yeah. Now, why did I do that? Because I wanted to write this program, which already worked for a while. Here I draw a coordinate system or coordinate axis. 2 even, because this is also about coordinate transformation. So we can hit enter here, and then it rotates. So now they are not as equal anymore as they were before. And in doing so, in order to draw this, I need to know where this point hits the rectangle. So we have a rectangle here for the window, and we have this hyperplane. Yeah, by the rectangle is the hypercube, not 4 dimensions but 2 dimensions. And this is the hyperplane of 1 dimension less, not 3 dimensions, but now just 1 dimension. And it intersects, of this line intersects with the edges of the hypercube in this point and in this point. And I want to find those 2 points. So I thought, well, but what if I have an n-dimensional hypercube and I intersect it with an n-1 dimensional hyperplane? Shouldn't I be able to do that as well? So that's why I worked 2 months on the code that I just showed. And once that was finished, I could also find these intersections. I feel completely, I'm a complete idiot. I'm just, yeah, but okay, that's how it worked. Even more, it was way more complex than that, because just finding those points is one thing. No, I had to know which point is the negative side of the axis. So we have a direction, because this is the negative side and this is the positive side. So I have a vector that points in that direction. And now I want to know, for an arbitrary rotation, where is the positive side and where is the negative side? So here's the negative side, here's the negative side, here's the positive side, here's the positive side. But after finding those intersection points, yeah, you know, and then in n dimensions, that wasn't easy. Long story short, I managed to do that, and therefore it also works now in 2 dimensions. So my code algorithm finds not only that it intersects here, but also that the axis goes from there. There's an entry point of this two-face, aka rectangle, or well, I don't think I can't. Oh, I can actually do this. Can I make it a square? I mean, internally it is just I index the corners with I call this 0, 0, I think, and then 1, 0, 1, 1, and 0, 1. And but those are just an index into an array with the actual coordinates. So 1, 1 is an index, and then that index is being used to look up the real coordinates, which could be I don't know, 300, 200, if it would not be exactly a square, for example. But we can work in the coordinate space of the indexes. So in the end, you just have to think of everything as being a square, and my tesseract is just a tesseract with edges with side 1, because we work in the index coordinate space, as it were. So yeah, I mean, just linear scaling, right? I mean, it doesn't matter. Well, that's not completely true, I guess, because if I do this, it cuts it in this one, and if you do that, it cuts it here. But nah, I mean, oh, let's see, I was right. It doesn't. Of course, I could have seen that immediately. There is no scaling at all. It just uses the fixed window size, so I can't resize the window afterwards. Just have to put it like this. But my story still holds. Okay, well, I guess that's it. Now on to the previous project that I was needing this for. I think I was working on this in order to write a how-to on a Q-transform coordinate transformations that I was working on. So not even something for myself, but more for, hey, I did all this work on coordinate transformations. Let's write a little how-to, so other people can learn this as well, understand this as well. And in order to write that how-to, I needed images, so I wrote this so I can make those images. However, my memory is so bad, if I don't work on something for a while, I forget it again. So I don't think I can write that how-to anymore, because I haven't the faintest clue what it was about, let alone all the details needed. to explain those coordinate transformations again. But yeah, I still have the code, so maybe if I look long enough at the code, it will refresh my memory. The code should be used. I think I can just continue rotating, then it stops. Oh no, it's completely dead now. So this program should be using it. And yeah, mirror is stuff. I have coordinate systems, centered, pixels, painter, and each thing is tied to a certain coordinate system. So this point is in painter, in the painter coordinate system, and this point is in has centered coordinates, and so on. And you can transform them by multiplying like that using a transform. So this thing ends on painter because it is in painter coordinates, and then I multiply that from the right with painter transform centered, and then this falls away, and then we end up with painter origin centered. That's basically how it works. So that way you can do all the coordinate transformations, I guess. And then the transform that is being used here is a wrapper around the Q transform. Okay, I'm gonna quit this video. Yeah, ridiculous. I should not have. Oh, it's half an hour. I thought it was longer.